Hey, good morning, everybody. This is Mr. Ainsworth here, and we're going to continue our study on how to use inverses to solve trig equations. And in my last video, part one, which you're looking at right here, we went through 4 main examples of how to apply techniques to solve trig equations using inverses. And today, what we want to do is go into example 5 and apply these techniques to solving a real problem in context. So here we go. This deals with a Ferris wheel. All right, so Jack decides to ride a Ferris wheel at the amusement park. His distance above the ground in feet after t minutes is given by the following function. Okay, so already I know that time is in minutes, and I know that my function y of t is in feet. Okay, so I know my units of time and distance. Okay, every ride is 3 full rides or 3 full revolutions of the wheel. So they go around 3 times. Okay, so keep that in mind as well. All right, the first thing we have to do is analyze the function. All right, and that we know how to do. So let's do that, okay? So we know the general form. We got A here for the amplitude, we got B, and then we've got our shift right here. There's no horizontal phase shift right here, but there is a vertical shift, and that's your K value. All right, so we want to find the information. We want to analyze the function and basically go through all of it in detail. So let's do that. All right, so here we go. So the amplitude, you always take the absolute value of the A value there because the amplitude is positive number there. All right, and it is 20, all right, up and down from the wave axis here. B is pi force, all right, period for cosine is always 2 pi divided by whatever B is, all right, so we want to substitute that in, and we have to evaluate 2 pi divided by pi force, and as you guys know, we want to multiply by the reciprocal, so my period is 2 pi times 4 over pi multiplied by the reciprocal, and then of course the pi's cancel, giving you 8, so we know the period is 8. Okay, now the shift, as I said, there's no horizontal phase shift, but there is an upshift of 23 units up there. So my overall shift is 0.23, or simply up 23. And that tells me that I know the midline, because the x-axis, which is typically the midline, if it's not translated, if you shift everything up, well, guess what? The new midline is y is equal to 23, according to the function. Okay, so this value here gets translated over here. All right, so how many minutes does it take for one ride? Okay, or how many minutes does one ride last? Okay, so let's get started here. So we know it says every ride is 3 full revolutions. What I need to do is look at the period here, right? And so the period is found by taking a look at, well, let me see. Well, we take 2 pi, all right, divided by b. I kind of did this already. B is pi force, so 2 pi. Let me start over here. There we go. So we want to take a look at the period of the Ferris wheel, okay, how fast it's turning. So I take 2 pi divided by b. There we go. 2 pi divided by b is pi divided by 4, and as I talked about earlier, that's 8. So what does that mean? Remember, time is in minutes and the distance is in feet. So this is 8 minutes for every revolution. Okay, so because the time is in minutes, and per 1 revolution. So 8 minutes per 1 revolution. That's your period. How does that get translated? How long is the ride? Well, it says every ride is 3 full revolutions. So we're going to multiply this by 3 right here, and so we get 24 minutes. Is equal to 1 ride. Now that's important because in part C, we want to find all times, all right, t at which Patty is exactly 40 feet off the ground, okay, during this 24-minute ride. So let's just keep that in mind right here, that the ride length is 24 minutes. So during the 24-minute period, okay, or 24-minute ride. Okay, so let's do that. So what we want to do is take our function up at the top right here, all right, and we want to figure out when is it 40 feet high. And guess what? That's y of t. So this information here, that's your equal to y of t, because y of t stands for a height function. Okay, they should have called it h of t. Like if I wrote this thing, I would have said h of t for a height function, but it says y of t. So just go with the flow. All right, so now we've got, let me write the function. We've got y of t is equal to -20 times cosine here of pi force t, all right, plus 23. Well, this is the height, okay? This is a height function. And because of that, we are going to substitute in 40 and try to solve this equation right here. So when is 40 equal to -20 times cosine of pi force times t plus 23? Okay, and we're going to try to do it using the techniques we learned on the front side. So and try not to use, graphing calculator here, which you could do. We'll do that too. No problem there. In fact, that'd be a good idea. So we'll do it using graphing calculator afterwards, perhaps, and then verify our answers. We could do that if the video doesn't run too long. Okay, so let's get started here. So what we want to do is isolate your trig function. Let's go ahead and subtract, add the opposite. So isolate your trig function. 40 minus 23 is usually 17. So 17 is equal to -20 times cosine of pi force t. And then, again, you're trying to isolate your trig function here. So a good idea, it would be to divide by -20. All right, simplify a little bit, and we get this fraction over the right, but don't worry, no problem there. And that's going to be equal to cosine of pi force t. We're trying to solve for t all the times. So remember this, we're going to find all times t, where it's exactly 40 feet off the ground. Okie dokie, so now what we want to do is we have to take the inverse cosine here. So take the inverse cosine and set it equal to pi force t, because this is our angle. So let me make a little note here. This is what we got to find. This is an angle. All right, and so to solve for pi force t, we got to take the inverse cosine. So using the inverse here, let me just make a note of this. So take the inverse cosine. Okay, that's how you solve for your angle. So to do that, here we go. So my angle, pi force t, is going to be equal to the inverse cosine of my ratio, -17/20. And I got to figure out when is this, what are the possible values here? And so notice here that we're taking the inverse cosine of -17/20. This is negative right here. So notice that. And you got to be thinking, what quadrants is this negative? Okay, and it's negative in quadrants, cosine is negative in quadrants 2 and 3 here, as you guys know. So I'm going to say quadrant 2 and then also a quadrant 3 angle. And the question is, what are those two angles? And whatever they are, then I use them to solve for t. So here we go. So pi force t is going to be equal to some angle in quadrant 2. So I'm going to use Desmos here just because I'm on an iPad. All right, you guys can use the T84. That's fine. Just set it to radian mode, and so we can work with it here. So I click on the wrench. I'm in radian mode. So I'm going to take the inverse cosine of -17/20 and see what happens. Okay, so what do we get here? So we get 2.587. All right, so let's see that. So our angle in quadrant 2, our first angle that we have, all right, is 2.587 radians in quadrant 2. Okay. So now how do we get the one in quadrant 3? How do we get from quadrant 2 to quadrant 3? Well, let's go over here to the unit circle just for a second here. So let me use an angle that kind of makes sense. Suppose the angle is actually 120 degrees. So look at the diagram here. You're in quadrant 2, and the question is, how do you get from quadrant 2 to 3? So what do you do with 120 degrees to get to 240 is what I'm asking here. So what you can do to get from 120 to 240, so from quadrant 2 to 3, you can take your angle theta and subtract it from 2 pi if you're in radians, or subtract it from 360 degrees if you were in degrees. Okay, so, and I noted that at the very top here. So let me do it for another example. Let's say we're dealing with 150, all right? So let's say quadrant 2, we're dealing with a 150 degree angle. To get to quadrant 3, 150 degrees, it should be, okay, 210 degrees, right? So from here to here. So let's take 360 minus 150, and guess what? That's 210 degrees. So what you want to do is you want to take, if you're in radians, take 2 pi minus theta. So 2 pi minus theta, whatever theta is in quadrant 2. And actually, let me write it this way. So if theta is in quadrant 2, okay, quadrant 3 would be 2 pi minus theta, or 360 degrees minus theta. That's a better way to write it. All right, so let's apply it over here. So in this case here, we're in radians. So we're going to take 2 pi minus this number here. So 2 pi, this is your method, minus 2.587. By the way, there's a different way to do this. So if you want to explore that, let me know. We can do that. All right, but those, we need a number here. So let's go back to Desmos again. So because I got to subtract it from 2 pi. Okay, so let's do that. So let's enter the number in. So 2 pi minus the 2.587. All right, and it's about 3.9. Oh, I did write that down correctly. 3.696. Yeah, that's close enough. All right. Now what do we do? Well, we got two equations really, right? All right, so I need to solve, okay, I need to figure out when is pi force t equal to 2.587. Okay, I also need to figure out when pi force t is equal to 3.696. Okay, and that's easy. Okay, so what we're going to do is you're just going to multiply by the reciprocal. Okay, so do that. So t is equal to, again, multiply both sides of the reciprocal. So actually, let me write it this way. So multiply this side by the reciprocal, which is obviously 4 over pi, and then multiply this by 4 over pi, which is the reciprocal. And what do we get? We get t is equal to this number. So once again, bust out the calculator, or the T84. Let me just keep this calculator off to the side. There we go. All right, so we're going to enter in 2.587, and we're going to multiply it by 4 and divide it by pi. So times 4 divided by pi, we get a result. So that's 3.294 rounded. So 3.294. And this is minutes now. All right, and over here, do the same thing. We got to multiply both sides by pi. So, 4 over pi. And over here, 4 over pi. There we go. And then figure out what that is. So let's take 3.696, all right, times 4 divided by pi. And we get about 4.706, okay? So 4.706 minutes. And then we got to figure out all times. So now take a look at this, okay? We got to figure out all times t, which Patty hits 40 feet off the ground, because this thing rotates 3 times, right? Okay, and what's the period length? We go back up to the very top here. The period length, all right, is 8 minutes per 1 revolution. That is the key right here. So 8 minutes per 1 revolution, that's your period. And as you guys know, periodic functions repeat if you add multiples of the period. So what we're going to do is we're going to add 8 minutes. And we're going to keep on adding 8 minutes until we get out of the 24-minute range. Okay, because the ride's only 24 minutes long. So my next time is 3 plus 8 is 11, so 11.294 minutes. And then you add 8 again, so add 8 again. 11 plus 8 is 19, so 19.294 minutes. Okay, and then if I add 8 again, okay, 19 and 8 is 27, so 27.294. But this is longer than the ride is going on, so we're going to exclude that one. Okay, it's longer than the ride. Okay, so again, you add multiples of the period. Add multiples of the period, which, as I said, is 8 minutes. Okay, so that's what I was doing here. Plus 8, plus 8, plus 8. It's periodic, my friends, and that's how you get multiple solutions. Okay, now over here on the right, 4 plus 8 is usually 12. Okay, so we have another time. Add 12, add another 8. Again, add 8 to 12, you get 20.706 minutes. Add another 8, and you get 28.706 minutes. But as I said, the ride's only 24 minutes long, so this one doesn't count. Okay, so we have actually 6 solutions. All right, 1, 2, 3, 4, 5, and 6. 6 solutions. 6 times that she reaches 40. 6 times that she reaches okay, 40 feet off the ground. All right, there we go, my friends. And that is how it's done. Okay, now the only thing I said is, you know what? Let's do Desmos action here. Let's confirm. Let's see. Okay, this ought to be good. This better happen. Okay, so I'm going to enter my function in. So here we go. This is a drum roll. So y equals, all right, negative 20 times the cosine. Let's bring the cosine function, pi divided by 4. All right, multiply that by x here, and then add 23. Okie dokie. So I've got my function in here. My y value is 40, so I need to say y equals 40. And then scale it properly here, and then take a look at the graph, and hopefully I'm right. Okay, so here we go. Drum roll, please. So here are the times right here in yellow right up there. So there's the first time, that's correct. Second time, that's correct. Third time, fourth time. Ooh, these are looking good. All right, fifth time and sixth time. Ooh, oh yeah. Okay, there we go. They are correct. And that's how you check, my friends. All right, so if you want to check using Desmos, be my guest. But there you go. There is a full-blown application problem. And that right there, you should expect to be able to do by test time, okay? And so practice this one. Set it a goal to fully understand a problem like this so you can apply what you learn. Okay? And I will see you in class. We'll do these problems in class, and I'll post solutions, obviously, in Canvas. But go ahead and give it your best shot. And again, this is Mr. Ainsworth here showing you how to do application problems using trig functions. See you there. Make yourself proud. Work hard, and I'll see you in class.